This is a black hole. It was simulated in C++ and CUDA. In this video, we will discuss how this was done. Black holes are celestial objects with masses concentrated in a small volume, resulting in an extremely strong gravitational pull when you get close enough to it. How light rays bend around a black hole as a result can be worked out by solving the null geodesic equation, as derived from Einstein's law of general relativity. And that is what results in the warped yet mesmerizing images of black holes.
Now, I have made some simplifying assumptions to make my job easier. I assumed a non-rotating black hole and neglected the Doppler shift associated with a spinning accretion disk.
Now let's talk about ray tracing. Say you want to create a 1920 by 1080 image of a scenery. You do this by shooting out light rays from a single point behind the said image. You aim a ray of light at a pixel from this point, then let it propagate forward. You find out where the light ray hits the scenery. That will determine what color value to assign to that pixel. You repeat this for all the pixels, and you get a picture. This process simulates a pinhole camera. You move the camera, generate hundreds of pics for hundreds of different camera positions, and now you have a movie.
For a black hole, instead of straight light rays, we use curved light rays. In order to compute the trajectory of a photon with a provided initial position and direction, we work in 2D polar coordinates on a plane formed by the initial position and direction vectors of the photon. We solve the simplified path equation derived from the null geodesic equation using the RK fourth-order method, then convert the interesting points in the trajectory back to 3D coordinates.
Let's look at some code, shall we? These are the constants used in our simulation. The universal constants of gravity and speed of light are taken as 1. The value universe radius is the maximum distance from the origin, beyond which I terminate the RK4 iterations. The function setBlackHoleConstants sets the various constants associated with the black hole, taking mass as the input, which I usually set as 1, but can be varied for a cinematic effect.
These are the functions to compute the derivative and initial conditions of any given photon, with an initial position and direction of propagation. In order to compute the photon trajectory, we first transform our coordinate system so that the x and y directions are present in the plane containing the vectors representing the position and direction of the photon. This allows me to convert any point in space to the 2D polar coordinates on the plane and back.
The next piece of the puzzle is the background. When the ray hits the universe boundary, I use a StarMap downloaded from NASA's Scientific Visualization Studio to calculate the color value for the pixel corresponding to that ray. Here is what the rendered visuals look like.
The last piece is the accretion disk. I use a function to check if the photon is present inside the accretion disk. Depending upon the photon's position within the disk, I modulate the density, transmittance, and luminosity of the disk, while also including Perlin noise to give the disk a turbulent look. Add rotation on top of this, with its angular velocity changing with distance from origin, we get the final look.
In order to make the videos, I render thousands of frames while leveraging GPU computation to render thousands of pixels in parallel. I save the frames as PNG images and use a command line tool to collate the images into video clips.
Now it's time to see some visuals.
That's all there is to it. If you found my video useful, please like, share, and subscribe. See you next time.